Hello, everybody, and welcome to the last topic of the semester, statistical mechanics. So statistical mechanics often gets a little bit of a bad rap, but really what we're going to be doing in this section is trying to dive into some of the concepts from thermodynamics that we talked about earlier. As you might remember, many of our thermodynamic principles were derived more or less from empirical observations of real physical systems. However, one of the things that would be very nice to be able to do is to be able to look at matter from essentially a molecular or atomic level and trying to build those thermodynamic principles up from what's often called ab initio or first principles. So, using just basic laws of physics, is there a way to get from molecular motion to thermodynamics? And that's really going to be the drive of this chapter. So again, classical thermodynamics doesn't even require the existence of atoms. All it requires is empirical observations, which we use to be able to build up pretty much everything we've talked about this semester. However, if we want to really figure out more about the atom level behavior of systems and get some of those nuances that thermodynamics often misses, we have to essentially start from the ground up. Unfortunately, in chemistry, that's slightly problematic as the ground up involves atoms and molecules, which are entirely dictated by quantum mechanics. So it's worth being able to make note of a couple of the take-home messages from quantum mechanics. They're going to prove really crucial in building up statistical mechanics. Some of these you'll be familiar with, some may be a little bit less familiar. So first of all is that great assertion that we now take for granted, pretty much that all matter is made up of many molecules. The part here I really want to emphasize here is this idea of many. Because when we're talking about chemical behavior, we're talking about systems which have Avogadro's number of molecules. That's 10 to the 23rd. So being able to talk about what any individual molecule or atom is doing is a little bit kind of facetious, as we'll almost never know. Instead, what we're really going to have to look at is more of the group or net behavior of this rather large group. And again, one of the other important things to keep in mind is that each of these molecules in turn is being composed of atoms, sometimes one or two, sometimes hundreds or even thousands. Now, a lot of the behavior of the molecules is going to be driven by a very important first principle. And that's this idea that atoms are in constant motion. So you are never going to find just an atom sitting stationary. It's always moving. And in turn, that means that these molecules are also always moving. And this movement is going to impart certain types of motion and energy. Now, one of the important things that's dictated by quantum mechanics that seems a little bit odd to a macroscopic view of the world is that it turns out that only certain movements are allowed. It turns out that you can only essentially translate or move in three directions at very specific speeds. Only certain rotations are allowed. Otherwise, you get essentially these wave particles that are atoms and molecules can start getting certain degrees of interference. And to avoid that interference, only certain speeds of motion or directions are actually going to be allowed. And this means that if I'm only allowed to have only certain movements are allowed, this means that only certain energies are going to be allowed. Because each of these motions are going to have their own related energy, essentially given by our good old friend mv squared. If you know the velocity and the mass of the object, you should be able to back out the kinetic energy. Unfortunately, part of the problem with that is if I'm only allowed certain movements or speeds, this means I'm only allowed certain energies. So all of these motions are going to be divided into discrete energy levels. And these discrete energy levels are going to kind of throw things a little bit off when we're trying to determine the behavior of a system, especially when we account that we also are going to have certain degrees of electron arrangements or movements. And these are also going to be divided into distinct energy levels. So we now have a whole bunch of different energy levels we have to worry about. And we're going to divide them into four major categories that we're going to be talking about the remainder of this chapter. And again, we're going to try and build up from first principles next semester in PChem 2. However, our first major movement is one that we're quite familiar with from the beginning of the semester, which is translations. Because it turns out that any molecule can move in three dimensions, the x direction, y direction, and z direction. But also, if you have more than one atom, you also have a certain degree of rotations allowed. As we've talked about before, you have 2 rotations allowed if you're a linear molecule, 3 if you're a nonlinear. However, if you also have more than one atom, each of your bonds can also have a certain characteristic vibration. And in fact, you're actually going to have many vibrations, which we'll again talk about a little bit later. But each of these vibrations is also going to have its own related energy. And one way to think about this is that since all of my atoms are in constant motion, we also have to worry about them being in motion with respect to each other. So these 2 oxygen atoms can essentially try and move away from the carbon atom and then move back towards. Well, this movement back and forth fits a certain kind of energy description called the Morse potential. And it turns out that to avoid essentially quantum mechanical interference, only certain velocities of rotation or of vibration are going to be allowed. And this gives us our vibrational energy levels. Now, it turns out that the Morse potential is a little bit inconvenient to work with, so we're often going to describe our system with a harmonic potential. If you've had physics, this is going to be familiar as a spring model, because this is the same exact sort of potential that we fit to objects moving back and forth on a spring. And so we can describe essentially each of these vibrations as behaving like it's on a spring. And this is going to do very well for to describe the vibrational levels that are most frequently occupied, essentially these near ground state ones, which we're going to be focusing on a little bit later. And then we have our final type of energy levels, and these are electronic. So with our electronic energy levels, these are essentially given by good old-fashioned molecular orbital theory, which you might remember from Gen Chem. Each of the electrons are going to be put into a molecular orbital with a discrete energy. Now, one of the important things to keep in mind about these energy levels is which ones are close together and which ones are far apart. As you may imagine, the translational energy levels are very tightly packed. Their energy separation is very, very small. However, by the time you get to rotations, these become slightly further apart, and it's much easier to observe discrete rotational energy levels. Vibrational energy levels, you should already be fairly familiar with measuring, because this is exactly what we measure using infrared spectroscopy, as you're literally watching how much energy it takes to move from, say, one energy level to the energy level directly above it, whether it's the 0 to 1 or 1 to 2. This characteristic absorption frequency is what makes up an IR spectra. Electronic vibrations are even higher energy, and this is what we monitor using UV vis. So again, in terms of small separation to largest, translations, rotations, vibrations, electronic. However, one of the things that's very important about knowing that we have these multiple different types of energy levels with distinct energies is that it means that I can break down the whole molecular energy for the entire molecule into these discrete energy levels, which we're going to represent as EI, where the molecule is going to be in state I with characteristic energy E. And we've already observed the importance of having different energy levels on observable properties in kinetic gases, as each different energy will result in a discrete pressure applied to the applied to the container that the gas is contained. And so we're going to be applying a lot of these same principles we developed for the kinetic gas, but more for a bulk ensemble and for other properties. So one of our key goals using StatMech is going to be trying to use these energy levels to determine how probable it will be that a molecule is going to occupy any given energy level. Now, if I know how probable it is for any given molecule to occupy any given energy, then I can try and scale these up to macroscopic systems by using what's called an ensemble. So this is essentially a statistically averaged ensemble of n molecules, where if I've got n molecules and I know the probabilities of each molecule being found in any given state, I can get a distribution of these are going to be the energy levels I would expect my molecules to be found in. Some high energy, some low energy, some in the middle. And trying to figure out the exact ratio of those is going to help me describe the system. And once I have this averaged ensemble, then I can use this to try and determine and predict all the macroscopic phenomena, such as internal energy, entropy, free energy, that we've really spent our time working with earlier in the semester. So this is going to be another way to hopefully rederive the equations we already had. So next time, we're going to go ahead and get started by looking at some of those energy levels and how I can put molecules into them. Until then, take care.